recursive decomposition in binary multipliers. The whole story starts from Karatsubha algorithm, and considering an example like x, for supposing 1 2 3 3 2 1, another on the other hand another number y equal to some 4 5 6 and 6 5 4, for example, this number could be divided into two halves, could be decomposed like this is what they say as divide and conquer thing. Like it can be divided into two halves giving the names A and B, another one C and D, and when it comes to that of some authors, the notation will be, it will be number A with AH and AL, this will be B with BH and BL, and this notation you come across in papers, and the reference paper which I worked on is given in the description box for your reference. You can find it over there. And when we multiply, this x could be more generalized, this number x could be more generalized. For example, x could be x can take the form 1 2 3 0 0 0 plus 3 2 1, isn't it? The same thing like addition. And remember, it's a decimal number. We are still not working on a binary. It's still a decimal number. And more precisely, 1 2 3 into 10 raised to 3. All right, 10 raised to 3 plus 3 2 1. And this can be reduced, compact, and it can be written more generalized. Guys, see, it's a here n equal to 6 over here, 1 2 3 4 5 and 6, the number which we are working on, and here it's 3. In the sense, it can be written as, if it is n equal to 6, now this will be n by 2 in general. So this can be written as 1 2 3. 1 2 3 is A into 10 raised to n is 6 and it's 3, so it can be n upon 2 half of n plus b, which is x. All right, the decomposition which we go for. And on the other hand, y will be in the similar manner. Y can be written as c into 10 raised to, again the same pattern over here, the same pattern like 4 5 6 0 0 0 plus 6 4 5, the same pattern. And so once again we are dealing with 6, n equal to 6 over here, 1 2 3 4 5 6, and here it appears 10 over 3, so it's 6 by 2 in the sense, n by half of n again plus d. All right, and when we compute the multiplication x into y, we have a into 10 raised to n by 2 plus b it's b. All right, it's b multiplied with the y number, the number y, c into 10 raised to n by 2 plus d. So multiplying each and every term with this one, with this x into y, we have a into c, and here a into c into 10 raised to n by 2 into 10 raised to n by 2, that gives us 10 raised to n itself, plus this into this, it's a into d into 10 raised to n by 2. We are done with these two. Again b into c, isn't it, plus bc into 10 raised to n by 2, right, 10 raised to n by 2 with this one, b into c into 10 raised to n by 2 plus bd. So this is the expression we come across recursive decomposition when we work on multipliers. And on the this could be even more simplified. Like previously we had another notation over here. What was that? What was the number? It's a 1 2 3 3 2 1, which was decoded as a b, and the second number, what was it? 4 5 6 something and 6 5 4, which was again decoded as a b, c and d. On the other hand, in papers which we find ah, al, bh and bl. All right, so this a into b, the same thing, like this can be decoded as x into y, that will be equal to ac. Guys, a into c, see, a into c, ah, bh, a into c, a into c, a into c, ah, bh, it's a ah, BH, and we have this one into 10 raised to N plus AD. What terms? A and D comes. AHBL, AHBL and 10 raised to N by 2 plus B into C. B into C in the sense ALBH, and we have this B into C, BC, ALBH into 10 raised to N by 2, and finally plus BD, B into D, ALBL. It's a ALBL. This is the notation which we come across in research papers. All right, we start with ABCD, for example, and then these expressions are usually found out in when we work on recursive multipliers, right? And on the other hand, this can be even more simplified. For example, like we can still simplify this one. And thing is, guys, this was started for a decimal number. Remember, we started with a decimal number in the sense the base is 10, and so we went for over here. If we are working on binary numbers, the base will be 2, and then this takes up the form x into y. That will be AHBH plus ALBH into instead of 10 we have base 2 raised to N plus AHBL into 2 raised to N by 2 plus AHBL 2 raised to N by 2 plus ALBH into 10 raised to, no, it's no more 10, I'm sorry, like the conversion for, we started with a decimal number, and what if for a binary number? So the base will be 2, here the base will be 2, when here the base will be 2 raised to N by 2 plus ALBL. Oh, and all these are known as shift factors. These are known as shift factors. And if you are working on any 4-bit number, 4-bit binary number, make a note of this one. When we work on 4-bit binary number, the equation takes the form x into y. That will be, and AHBH and 2 raised to 4, isn't it? 2 raised to 4, n will be 4, it will be, the shift factor will be 16 over here, 16 times AHBH as it is. When we work on 4-bit binary number, n will be 4 and binary, so it's 2, the base is 2, and 2 raised to 4 it's 16, AHBH plus, and this factor 2 raised to half of this one, 2 raised to 2, that will be 4 times AHBL plus, even this will be 4 times ALBH plus ALBL. This will be the expression for the product A into B or XY, where all these functions, all these values are known as shift factors. All right, all these known as shift factors. And a small working example from the reference paper I have taken. Considering 2 binary numbers, all right, considering 2 binary numbers, and with this very expression, trying with this very expression, the values, the numbers, the binary numbers they have considered is, one is with this very expression, of course, with this very expression, they have considered 2 numbers like x equal to what they supposed is 1 1 1 0, and another number is 1 0 1 1. Now they decomposed into 2 separate, they started dividing and conquer, this half and this half again. Let's give the same notations, like if it is A, we'll have AH and AL. If it is B, supposing this to be B, this will be BH higher order and BL lower order separation. And 1 1 decimal, like binary 1 1 is I guess 3, it's a 2, it's a 2, it's a 3. and making use of this very expression. All right, so how the decomposition is used in recursive multipliers. So let's check. Let's go for the binary multiplication between these two. 1 1 1 0 multiplied with 1 0 1 1. So here we go, like 0 1 1 1. We have a offset over here. 0 1 1 1 again. We have two offsets over here. We have 0 1 1 1 over here, and we have three offsets, 1 2 3, and 0 1 1 1. Don't get confused. This one is multiplied with this, it's a 1. This number is multiplied with this, it's a 1. This number, this one is multiplied with 0, and so we don't have this anymore. We don't have this anymore. And once again, the whole, this complete number 0 1 1 1 0 1 1 1 is multiplied with 1. Yes, we have this one. Now adding this, it's a 0. All right, it's a 0, and what, it's a 1 plus 0, it's a 1 1 1, it's a 2 in the sense 0, and 1 over here, it's 3. 1 plus the carry, the previous carry, 1 plus 1 plus 1, it's a 3 in the sense 1, and 1 over here, it's a 1 plus 1 plus 1, it's a 3 again. 1 carry 1, it's a 2. 1 plus 1, it's a 2, so 0 and 1, and 1 plus 1, it's a 2 with the sum 0 and a carry 1, isn't it? So this is generally what happens with the binary multiplication over here. Let's cross check if this really works with this one, this very same. And what do we have over here? And the result is 1 1 1 0 multiplied with 1 0 1 1. Guys, it's a 2 raised to 0 over here. It's a 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, and finally 2 raised to 7. In the sense, what all can be removed over here? Into 0, we don't have this anymore. Into 0, we don't have this anymore. 2 raised to 2 into 0, we don't have this anymore. And this also can be. Guys, I need a calculator at this point to make a confirmation on this one. All right, it's like 2 raised to 7 plus 2 raised to what? 4 plus 2 raised to, it's a 3 plus 2 is left over again. So the resultant from the binary, traditional binary multiplication, adding all these, it's a 154. It's found out that 1110 multiplied with 1011, it's a decimal one converted here. This is the binary like thing. All right, the binary and the decimal equivalent, it's 154. Let's check if is this really we obtain the same value making use of this decomposition. All right, so it's 154. Remember, I need the place over here. It's a 154 over here. It's a 154 when multiplied with this one, and plugging in the same values, like what do we have here? AH, BH, AH and BH, in the sense 3 into 2. What it is? It's a, guys, we are working on binary numbers. The base is 2 and n equal to 4 over here. 1 2 3 4. So this takes up the form like a 2 raised to 4. It's 16. I'm sorry, I erased this one. So once again writing that one. AH, BH plus it's 2 raised to n by 2. 2 raised to 2, it's 4 times AH BL plus, it's again 2 raised to 2, it's a 4 times AL BH plus AL BL. Once again, let's take the, once again we have AH, AL, BH, B, etc. all these over that side, and plugging in those values whatever we have decoded for that one. It's 16 times 16 into, like 16 into AH BH, 3 into 2, 3 times 2 plus for this one. All right, for this one, and here we have 4 times, we got to go for 4 times, it's a AH BL, AH it's 3 into BL, it's 3 plus 4 times AL BH, AL it's 2 into BH, BH it's 2 again, plus ALBL, it's 2 into 3, isn't it? 2 into 3, and here we go 16 times 3 to the 6 plus 4 into 9, here 4 into 9 plus 4 into 4 plus 6. At this point I need the help of a calculator, guys. Hold on, we may, yeah, almost we are done, almost over there. 16 into 6 plus 4 into 9 plus 16 plus 6. Yeah, the answer is here 154. The binary 154, the binary decoded, it was 154, and even with the decomposition it's 154. This is how recursive decomposition is obtained in recursive multipliers. Thanks for watching.